Thank you so much. It's an enormous pleasure to be here tonight with you to give you a brief overview of some lithium-ion battery work and just a little bit of a history of lithium-ion batteries. And where best to start but with the immortal words of Julie Andrews. We should start at the very beginning because it's a very good place to start. The Big Bang. So this is the moment at which the universe as we know it was born, and the moment at which each one of us was connected to each other atomically and to the rest of the universe atomically. One of the fundamental laws is the first law of thermodynamics, and it really thinks big, that energy, the amount of energy needs to remain constant. It says that the energy cannot be made or destroyed, but it can be converted from one form to another. And it's this idea of conversion of energy that brings us here tonight to discuss devices like batteries that allow us to store energy in a chemical form and then transform that chemical energy into electrical energy as and when we need it. So before we delve into the geography of battery cells, let's take just a short history of how these batteries were developed. So the term battery was first coined by Benjamin Franklin. And it was in the backdrop of this, US independence that there was an experiment carried out that really shocked the world. Galvani, an Italian scientist, had long thought that there was a sort of link between movement and electricity. And in one of his experiments, he connected a lightning rod to a frog's leg and then waited. And when lightning struck that rod, the leg moved. And this really shook the scientific world, and it also provided it influenced Mary Shelley at the time, who was writing her novel Frankenstein. Now, it was after this, shortly after this, that Volta started thinking about, okay, Galvani thinks that this electricity is intrinsic to this frog. What about this electricity being intrinsic to metals? And he started looking at combining different metals together, connecting them, metals like iron and zinc together, to see if you could elicit some electrical current. And sure enough, he did. And it was this discovery of bimetallic electricity that formed the basis for his innovation, the voltaic cell. This is a picture of a voltaic pile, and this is housed here at the Royal Institution. And this inspired Michael Faraday, who looked at voltaic piles and started to construct his own. And in his first experiment that was noted here at the Royal Institution, he constructed a voltaic pile from halfpenny coins. And in 1814, Faraday visited Volta in Italy, and Volta presented him with a voltaic pile, which is the one that's housed here at the Royal Institution. And it's such a beautiful example of shared scientific discovery and knowledge. Around about the same time, again at the Royal Institution, was the first isolation of metallic lithium. Lithium, this is the name that gives itself to the lithium-ion batteries that we use today. And at the same time in history, electromagnetism was taking off. And inspired by this, Faraday looked into electromagnetism in a bit more detail, conducted a lot of experiments to try and understand this in a bit more detail. And in one of his experiments, which I just show here, he had a long wire that was, sitting inside a glass vessel that had a little bit of mercury metal in the bottom. And on the bottom of that glass vessel, there was a magnetic bar. And by connecting this setup to an external battery and charging that electricity through that wire, that set up a magnetic field along that wire. And that magnetic field interacted with that bar magnet. And that set up this wire to move in a cyclical motion. And that was the birth of the first electric motor. Following on from that, there were further discoveries in batteries from John Daniell, a British scientist who had made the first Daniell cell. And then following on from that was the discovery of the first rechargeable lead-acid battery. And this was by Planté, and this was used to light lights in carriages at the time. And of course, now in cars, it's used for ignition as well. It was Faraday who had really looked at this link between chemistry and electricity. And looking at the work that he did and the work from Coulomb, we can really start to understand electricity and chemistry and start to think about things in a quantitative way. Here I've just shown an image of Faraday's lab here at the Royal Institution, and also a picture of Faraday giving his Christmas lecture in this spot, because I thought that was a really sweet picture to show tonight. So Faraday, through his laws of electrolysis, had looked at how we can measure, we can think about electricity and think about the mass of materials that are involved in these sorts of transformations in electrolysis. And from that, we can work out quantitative information about our batteries. For example, the capacity of a battery. We can think of that as a measure of the charge that the battery can store. And this really depends on the mass of what we call active materials. These active materials are things like electrodes, and it was Faraday that gave us those names: cathode, anode, ions, cations, and anions, and electrolytes. We can think of capacity as sort of the maximum amount of energy that can be extracted from a battery under certain conditions. And we can measure this in a number of different ways, and we're going to hear about that later in some of the next talks. And we use, in our own labs today, we use Faraday's law of electrolysis to work out what the theoretical capacity of a battery material may be. And we strive to work towards achieving that theoretical capacity. So tonight's talks are really focused on lithium-ion batteries and lithium-ion battery chemistry. So we should look back over some of the key papers that brought about this wonderful discovery that powers our electric vehicles increasingly, our portable electronics. And one of the first publications here that I'm showing is from Lewis, a very famous chemist, who had looked at the potential of the lithium electrode. And some work had been started then in 1913 on lithium batteries, but the first lithium-ion batteries were not commercialized until the 1970s. In the 1970s, there was the first publication of electrointercalation, so the movement of lithium ions into and out of a material. And this is by Stanley Whittingham, who looked at titanium disulfide materials. This was very quickly followed by the pioneering work of John Goodenough, who had discovered lithium cobalt oxide, a material that's still used in our batteries today, which facilitates the movement of lithium into and out of these structures. He'd done this work at the University of Oxford at the Inorganic Chemistry Laboratory, which you can visit and see this blue plaque dedicated to him. And in the 1990s, Sony commercialized lithium cobalt oxide batteries. Very quickly followed reports of spinel-type materials, manganese spinels, and iron-based phosphoolivine materials. And this sort of research area remains extremely vibrant and exciting even today. So let's look at a lithium-ion battery cell in a little bit more detail, and we can break it down into its component parts. So this is a picture of a typical coin cell, which you may have seen in some of your devices. It's made up of a cathode, which is our positive end of the battery, an anode, which is the negative end, and then there's a separator that keeps the two apart. And between those, there's something called an electrolyte. We can understand what each of these components does if we start to hook this up to an external circuit. So this is my imaginary battery, and my cathode, my anode, and my electrolyte. So I have my positive cathode and my negative anode hooked up to an electrical circuit, and that permits this flow of electrons around this circuit. And because of the chemical reactions that are going on inside this battery, you end up getting a buildup of electrons at that anode. The electrolyte plays a hugely important role. It doesn't allow electrons to move from that anode across to the cathode. So the electrons are forced out of that cell around this external circuit. And on that journey, they can start to power things that they're hooked up to, like, for example, this light bulb that we have. So the electrons move around that external circuit and perform their function. What does the electrolyte do then? The electrolyte is what permits the flow of lithium ions in a lithium-ion battery. So it's ionically conducting, but electronically insulating. If we look in detail at this kind of cathode material, this is called lithium nickel manganese cobalt oxide, which is a bit of a mouthful, so we call it NMC for short. And the little letters that are after its name tell you a little bit about the makeup of that material, so how much nickel there is, how much manganese there is, and how much cobalt there is. And this is a material that's currently used in electric vehicle batteries. Each one of those elements plays a specific role in that battery. The nickel increases the capacity. Remember, that's the charge that our battery can store. But when you increase that nickel content, there are some challenges and complexities in the synthesis of these materials. The manganese provides structural stability, but it does so at the expense of the capacity of the battery. And then finally, we've got cobalt, which improves the rate performance, but as we're going to hear later on, is costly, and there are ethical concerns with mining cobalt. So let's look in a little bit of detail about how lithium ions move in these battery materials. So this is my NMC material. I've just blown up this structure a little bit more so you can see these layers of transition metal oxide, and these green dots here are my lithium ions. So this is my cathode material, and then on this side here, I've got my anode material, and a very typical anode material that's used in modern batteries is graphite. And graphite, again, because of that lovely layered structure, it allows the movement of lithium ions in between those layers. So during charge, we start to see the movement of those lithium ions from that cathode across to our anode. And they move through that electrolyte. And then during discharge, the lithium ions then can move from the anode back across through the electrolyte and into our NMC structure again. And that movement of lithium ions and the movement of electrons out in that external circuit, the electrons are moving in the opposite direction. These two things are interconnected. If you don't have one, you can't have the other. So for example, if your lithium ions stop moving because your battery is discharged, no more electrons in the external circuit. How do we know where all these atoms are? I've shown this beautiful picture of all these atoms perfectly arranged. It's hugely beneficial in the UK that we have these wonderful resources like the ISIS neutron and muon source and the diamond light source. This is where we use neutrons and high-energy X-rays to interrogate the structure of materials, and we can work out where in space all of these atoms are lying. We can determine if atoms are sitting in the right place, or sometimes they may sit in the wrong place. So over time, lithium and nickel, I didn't show this in the image, but lithium and nickel ions are very similar in size. And you may have noticed when you buy a new device that your battery works really, really well, but a year or two later, the performance isn't as good as it used to be. And that's because over time, those electrodes start to degrade a little bit. Atoms start moving into the wrong positions, your electrode materials start to crack, you start to just get the breakdown of your material over time. So what can we do to try and mitigate these degradation processes? Well, when we look towards the next generation of lithium-ion battery materials, and when we look at cathodes in particular, where are we moving to? We can increase the nickel content of these battery materials to try and up that capacity, try and reduce the cobalt, maybe even completely eliminate it. We can try to discover even new materials, and we can do that by combining things like computational insights from calculations with some synthetic design procedures and try and come up with a new family of materials. We can design strategies and develop strategies that avoid degradation and prolong battery life. And how do we do that? Well, sometimes we can form a protective coating around our NMC material, and that will protect it from some harmful species that might erode it over time. Or we can start, as crystal chemistry engineers, we can start to mess around with the atoms that are present, take one or two out and replace them with an element that might keep that framework structure nice and stable over multiple cycles. We could also look at making our batteries safer. These electrolytes that I've talked about up to now are liquid-based electrolytes, and that's what's in your mobile phones and your laptops. We could maybe move from liquid electrolyte systems to solid electrolytes and ceramics that provide greater safety and allow you to operate at higher voltages. So as we're moving to these next generation of lithium-ion cathodes, we have to start to think about where we're going to source these raw materials from. And I think this is the perfect time to start handing over to Simon, who's going to discuss the source of materials in a bit more detail. Thank you.
Thanks very much.
I'm going to talk about the rise of the battery megafactories. It sounds grandiose,
but it's been a trend that has kind of been unbelievable to watch the last 4 years for Benchmark. And that's where, as a publishing company, we spend all of our time in the supply chain from the mine to the battery cell, collecting data and advising these companies. So, big statement number one, we are in the midst of a global battery arms race. Again, sounds over the top, but it doesn't even begin to scratch the surface of what's been happening with the build out of global lithium-ion battery capacity in the wake of what people call the energy storage revolution, which really is pure electric vehicles and energy storage systems, off-grid energy storage systems. For this, I'll take you back to 2012, actually. Show of hands, how many people here know the name Elon Musk? Hands up. 5 years ago, that would be 10 people. I guarantee it. So Elon Musk, who is the CEO of Tesla, back in 2012, got on a plane to go to Japan to see the world's biggest lithium-ion battery producer, Panasonic. And he went to very conservative Japan, a very conservative battery company, to ask them nicely to expand their capacity by fourfold in 3 years, just so he has enough batteries to make electric vehicles that no one buys yet. What he wanted to do was he tried to convince them, he would sell pure electric vehicles in the hundreds of thousands a year when they were being sold in single-digit thousands back then. Really, it was only the Nissan Leaf back in 2012. He came back, he wasn't successful, surprise, surprise, and he devised a plan called the Tesla Gigafactory, which is essentially building the world's entire supply of batteries under one roof just for Tesla back in 2013, 2012. Well, in Q1, the plan was underway, and that sparked what we call this battery arms race, this race to build out enough capacity for this next generation of vehicles and storage. Well, today we've got 72 megafactories in the pipeline. That's in a 3.5-year period, really. And that equates to 1.59 gigawatt hours. I'll go into a bit more detail on that. In a chart form, this is what's happening now. You've got gigawatt hours on the left, and gigawatt hours is a way of quantifying, really, it's energy storage, but it's a way of quantifying how many batteries these plants can produce. It's important to know, of the 72, about 40 already are in production at multi-gigawatt hour scale. That is an order of magnitude bigger than their predecessors. So these battery plants are significantly bigger than what was being built just for your mobile phones, which makes sense really when you think a car is much bigger than a phone. This is where we're going by 2023. This is where we're going by 2028, and more of these plants being announced as we speak. One last week was announced in India, which we haven't got on this chart. So that will intensify as the world needs more batteries. How many electric cars, pure electric vehicles, does that equate to? It's about 22 to 24 million. So when you look at these big announcements, like VW this morning announced they want to build 70 now pure electric vehicle models by 2028, you realize that isn't a lot of batteries. We're going to need a lot more. So this is the Tesla Gigafactory. You've got, on the right is a picture. We were there last week, actually. So the picture on the right is actually Casper. I don't know where he is, here today somewhere. There he is, Casper. For scale, Casper's about 7 foot tall. So you can see it's a big plant, effectively. But the Gigafactory right now, and it's only a third of its design capacity, is bigger than the world's entire battery industry in 2014. On the left is, you can get scale from the size of one floor on the left, which is the little computer monitor at the bottom. So that's the size of a floor. There's 3 floors. On the right is some nice pictures of Tesla Model 3. This is a little video, and it actually goes further back, so it goes in the L shape, so you don't see the full amount here. This is in the middle of the Nevada desert, not very far from Reno, actually, so actually a great location. But nearly all of that, 75% of that is battery making. Only 25% is car and battery pack making. So really, the challenge here for all gigafactories, megafactories going forward is getting as much of the supply chain on one site as possible, reducing the logistics between all the components from raw materials to battery cell. So as you can see, this is the ultimate plan for Tesla, is to bring all the raw materials for the cathode and anode, as Serena explained, and then going into cell manufacturing on site, then literally making the battery packs, making the chassis, the motor, putting all of that together in one complete unit, and then you just got to bolt the metal doors on and seats and wheels and stuff like that. So 80% of the cars are going to be built on site, and this is the blueprint for all electric vehicles going forward. So this is what the UK must do, it has to do. It's what Europe has to do, and it's what China are pushing towards. So why are lithium-ion batteries so important? Well, if you think of a pure electric vehicle, this is not plug-ins, it's not hybrids. I'm talking about these, we don't have many on the road, but a pure electric vehicle where the whole chassis of the car is a battery pack. It's a lot of batteries that go into it. In fact, there's over 4,000 of these 2170 cells which Tesla produces at the Gigafactory go into a Tesla Model 3. Why are raw materials so important? Well, 79% of the cost of that cell are minerals and metals. So a smaller proportion are the cathode and anode raw materials, which are actually not commodities, they're chemically engineered input materials. They're a lot tougher to get into the supply chain, so that's something we can talk about later. But they're essentially what the industry call a jelly roll, which is like a Swiss roll, I guess, cake of minerals and metals. Then you inject it with electrolyte, and then you put it in a canister, and that's effectively the modern day cylindrical cell lithium-ion battery. I probably didn't do the science justice there. And as you can see, the Tesla Model 3, 25% of the cost of that car is the battery. So, statement at the top, the cost of batteries are the decisive factor for the successful failure of EVs. Tesla, by the way, is now producing those at under $100 per kilowatt hour this year. So that's another barrier broken. The bottom statement, the price of raw materials are the decisive factor for the cost of batteries. So this is why the raw materials are so important: scale, quality, and cost. So big statement number 2, the lithium-ion battery supply chain are the oil pipelines of tomorrow. What are the raw materials to watch? We like to call them the 4 horsemen of the ICE apocalypse. So that's the internal combustion engine, ICE, which is the cars on your road, for those that don't know. We've got lithium leading the charge. We've got the dark horse graphite, which doesn't get much kudos and coverage, but it's the anode material of choice. So it is so important that graphite keeps pace with the rest of this industry. Cobalt doesn't have a very good reputation. And nickel there, trying to kill cobalt because there's a trade-off with increasing nickel, reducing cobalt. We could talk about that a bit later as well. You can see coal and oil are dying a death at the bottom, and the house that ICE built being knocked down. But the 4 horsemen of the ICE apocalypse are quite like that. So final few slides. Lithium supply. I used lithium as an example, but we can talk about cobalt, graphite, nickel later on in the Q&A. Most of it, actually, a decent chunk of it is coming from Chile. This is the Salar de Atacama. It's actually brine mining, so low impact, where you're pumping brine out the water, evaporating the liquid away and extracting the lithium and other minerals, and then you're putting it through a processing plant. Actually, the majority of feedstock now comes from traditional hard rock mining in Australia. That's your traditional mining where you can get a rock concentrate. That gets shipped to China, and that then is processed into battery lithium within China. And again, the key thing to understand is lithium is a very small industry. Last year, 300,000 tons, give or take, produced. LCE, this is lithium carbonate equivalent. But all the commodities you're used to hearing about, coal, copper, oil, they're in the millions or tens of millions of tons. So lithium needs to get to well above 1 million tons by mid-2020s to keep pace with the demand. Don't think it's going to do that, but the point is that it has to go from the niche to the mainstream, and it's not a commodity, it's a specialty chemical, which complicates the supply chain a little bit more. So this is lithium demand. This is a big boy, Andy Miller. I put this in because his mum's here tonight. Andy Miller isn't with us. He's over in the US, but I thought Catherine would like that. Again, from a demand perspective, look to the right-hand portion of this supply, of this pie chart. Lithium-ion battery, 51%. It's important to note that now with these raw materials, it's the same for cobalt, it's similar for graphite, that the battery end use is now taking over the majority of the supply chain. So once you go past that 50% mark of this mineral being used in batteries, then the industry, the producers, the supply chain recalibrate everything they do towards lithium-ion batteries. That wasn't the case before, so that's something to bear in mind. Then they take the chemical out of the ground. On the left, they turn it into a white powder, effectively. That's what lithium carbonate looks like. On the right, they bag it, and then they will send it to the Tesla Gigafactory, for example, in this form, where they mix it with the other cathodes, the NCM or the NCA material, and then it goes into a battery. Final 2 slides. The reason it's complex and difficult is there are 5 stages. More importantly, there are 15 steps to get lithium out of the ground and into an electric vehicle. So there's 15 steps for it to go wrong, 15 ways to qualify that material, 15 hurdles it has to go over, so it's not straightforward. As a result, price volatility is now the norm. Lithium's price has increased 4x. It's come off since, but still remains high. And that's the same for cobalt and other raw materials going into a battery. There's a lot to talk about. Thank you for your time.
So really picking up from where Serena left off is all of that wonderful electrochemistry that drives the storage and the release of energy takes place in the form of a rather dull-looking particle about 5 microns across that's kind of black or grey. I've got some examples here. It's really nothing special to look at if you're not looking at it through a microscope. And if you wanted to try and get some power out of that, attaching leads and crocodile clips to those tiny particles is a bit tricky. So what we need to do is turn it into a format that we can actually get electricity in and out. And what we do is we coat those powders onto foils. We call the foils current collectors because that's what they do. And inside that coating that we put onto the foil, you can see on the micrograph behind me, lots of tiny little particles. Those particles are about 5 microns across. That's about 100th of the width of a human hair. And they're packed into a matrix of bits of carbon and some adhesives and some solvents that we use to be able to deposit them. And the purpose of those additives is to connect all of those little electrochemically active particles together and to connect them to the metal foil that sits at the back, because that metal foil is something that we can connect a wire or a light to in order to take some performance from it. And that structure is incredibly carefully engineered. If you think about the journey that Serena talked about, where the lithium ion has to travel across the separator, it then has to combine with some of those anode or cathode materials. It's a little bit analogous to trying to park cars in a car park. If you think of those particles, those electrochemically active material particles, as being a little bit like car park spaces, I can have a battery which stores lots and lots of energy by having lots and lots of spaces. So I can pack as much material into it as I possibly can. But the challenge is to do that, I'm sacrificing all of the roads and the channels through which the lithium particles are going to have to travel to find their parking spot. And so what I need to do is engineer this electrode to get just the right balance of accessibility of those particles with the total density and availability of them. And there's some really great technology goes into preparing what we call inks and printing those inks to do that. So what we do first is we take our powder and we mix it into an ink, and we mix it with carbon black typically, which is a nice conductive additive that links the electrical current all the way from the particle to the foil. And we'll mix in some binders, and that's basically an adhesive that makes the carbon stick to the foil. And then we use a solvent which makes it liquid so that we can start to print it, and we're going to dry off that solvent. And as we dry the solvent off, it's going to leave porosity behind it, and that gives us that beautiful microstructure that you saw earlier. So we coat, and I'll show you a video of that in a moment, on a reel-to-reel coater. To make the kinds of volumes that we're talking about, this is something that has to happen at very high speed. I'll show you some more details in a minute. But this is something that has to run on a continuous process line at about 120 meters a minute to be able to make the quantities of batteries that we need. And then we have to dry off the solvent, and that actually takes a tremendously large amount of energy. The solvents that we use for our anode are typically things like water. They're quite benign. But at the moment, we don't really have any good solvents for cathodes that aren't fairly unpleasant. We use a substance called N-methylpyrrolidine. Brilliant solvent, really horrible for health. So we have to be very careful how we control that in an industrial environment. And then we do something called calendaring. We run that very carefully coated microstructure through a world's biggest mangle. And what that does is it compacts it all down and it gets a bit more density in there to give us a bit more energy storage before finally we chop it into pieces. And once it's chopped into pieces, we can assemble it into cells. And we can assemble those cells in one of two typical formats. We can cut those cells into big sheets, like rectangular sheets, typically about the size of maybe an A5 or an A4 book, and we stack them like a lasagna. And what we're doing is trying to get as much contact area as possible between the anode and cathode sheets with those separator layers in between. And if I cut them as rectangles and stack them lasagna style, I get something that I call a pouch cell. The other way that we can do this is we can print it onto very long, thin strips, and we can roll those strips together. And that makes me a cylindrical cell of the 21700 sort that you saw in Simon's presentation. And I've brought a couple of those along with me tonight. So the battery industry is not very imaginative, so this is called an 18650 cell. That means it's about 18 millimeters diameter and it's about 65 millimeters long and it's about circular. All of those are actually about to an engineer. A 21700 is 21 millimeters by 70 millimeters. You get the idea, it's not complex. But what we've got inside this cell, if I was to open it up, is our roll of materials, all tightly packed. Don't do this at home, by the way. At home, this is full of caustic electrolyte, and it will do you no end of harm. Do it when you make these in the lab for fun, and you don't put the electrolyte in. But what you see in here is a roll, and in that roll, we've got the layers of anode and cathode material separated by this white separator material, polymer separator material. And that simply gets dropped into the cell can. We weld the electrode to the bottom. We weld an electrode to the cap. As Simon so eloquently put it, we squirt in some electrolyte, typically under vacuum, and then we seal the whole thing up, and we take it off and charge it for the very first time. And if you were to see what those foils look like inside, we can put about a meter of foil, a meter of anode and about a meter of cathode foil inside each of those cells. This is actually an anode material, so this is just made of graphite, which means I can handle it and it's safe. If I was to bring the cathode material, which has nickel particles in it, I'd have to wear some gloves and people would get annoyed from a health and safety perspective. So to see what that looks like in a lab type environment, I've got a short video here. Ollie, if you could just hit play for me, that would be brilliant. Thank you very much. So what you can see here starts off with the mixing process. This is done in a lab environment. This is not what a factory looks like. So we're mixing up that ink, which is a bit like a kind of molasses type consistency. We then pour it into a reel-to-reel coater where we lay that coating down onto a roller. We draw the foil up against it, and that draws off the coating to give us the coated foil that we're looking for. The drying actually takes place in a closed cupboard that you can't see, and then we stamp the materials. We use a robot to assemble them because we have to, the alignment of those anode and cathode foils is absolutely critical to the quality of the battery. It's one of the things that can cause it to fail early in its life. We then seal it into a material which is actually very similar to a coffee bag. Coffee bags resist moisture for about 3 months. That material resists moisture for about 15 years. And having done that with the electrolyte, we then take the thing off, ready to form. Now, in our laboratory, we can make about 20 cells a day using researchers. If you were to walk into a gigafactory, you'd see individual lines producing something more like 20 cells per second. And that's one of our challenges. And we don't just put those cells directly into the car. We first of all have to put them into sub-assemblies which are manageable. So we take our cell, whether it's a pouch or whether it's a cylinder, and we assemble them into things called modules. These are really just sub-assemblies. And what we're trying to do at this point is to keep the voltage of each of those sub-assemblies below about 60 volts, so it's relatively safe to handle. And we're trying to keep the mass down to about 50 kilograms or so that it can be handled in a factory environment. And ideally, we want that module to be reusable across many different electric vehicle types so we can get some economies of scale out of its manufacture. And then we'll join those modules together to make the battery pack. And the battery pack, you can see the Nissan Leaf one on the slide behind me, typically covers the whole of the floor of the vehicle, typically weighs somewhere between 300 and 900 kilograms. So it's a fairly substantial piece of equipment. And then that gets bolted underneath the vehicle, typically on the production line for the car. And the fact that that pack is large, it's heavy, it's hazardous goods, means that there's a lot of benefit to doing the assembly of that very close to where you do the assembly of the car. And that's important for us for reasons I'll come back to in a moment. So as Simon said, our Tesla Model 3 has about 4,400 of those little cylindrical cells inside it. And Tesla's finally reached its magic number of about 1,000 cars per day in manufacture. If you want to multiply that up, that means that just to produce one model of car, that factory has to produce 50 cells every second. And given that as well as the Model 3, they're also making the Model S, the Model X, and a whole bunch of other stuff besides. So actually the gigafactory that's there doing about 20 gigawatt hours today is doing about 125 cells per second. The fastest miniguns that get connected to helicopters by the RAF for shooting at targets, the very fastest that they've ever made that have gone to production are about 125 cells per second. It just gives you a bit of an idea of the rate that these factories have got to be operating at. And that's how you get to the things like the gigafactory. So it takes about 4 billion of investment just to get to the point we are today to do 20 gigawatt hours. And as Simon said, this is only about a third of what Tesla want to be doing in the long term. And that's already a 200,000 square meter facility with about 3,000 staff. So it's a fairly significant industrial endeavor. It's also a massive commercial opportunity, whichever way you look at it. So the reason that the UK is interested in all of this is the UK at the moment has a very good industry in cars and particularly in making engines. We make about 1.7 million vehicles and about 2.4 million engines every year. And the engine is about 1/3 of the value of the car, bill of materials cost. But when we move to an electric vehicle, we replace the engine with an electric motor and some power electronics, and that costs about the same as the engine. Then we put a battery in place, and that costs typically 3 to 5 times the cost of that engine, and then we put the rest of the car on top of that. So there are two things that you'll notice. The first thing is the total cost of our vehicle has gone up significantly. The second thing is that nearly 50% of the bill of materials cost for a long-range electric vehicle is embedded in that battery. If we see that as a bought-in component, that's outsourcing an enormous amount of the value creation that happens in the car industry in the UK today. So economically, as well as technically, it's important for that to be a component that we have an ability to deliver. If we look at the kind of volumes that Simon's slide showed around what we've got to get to by 2028, 2030, across the EU, we're going to need the equivalent of about 12 of those gigafactories at the size they are today. And to support the UK industry, if we supply it domestically, that's space for about 2 to 4 gigafactories of that size. Actually, there are some very good arguments that say that the economies of scale suggest you want smaller factories, probably about 10 at about half of that size. So that's a big opportunity for the UK. And in response to that, the Faraday Challenge and the Faraday Institution, which has sponsored today's event, has been set up to accelerate the UK's research efforts, our innovation, and in our industrialization of batteries, going from the achievements of Goodenough in the 1980s as the inventor of the lithium-ion battery to try to place us in the position where we've got large-scale manufacturing and exploitation of that technology coming from the UK. And that journey takes place over an enormous range of length scales. So the kinds of technology development or scientific development that Serena's talking about typically happen at the scale of milligrams or grams in a laboratory. As we look to see whether they work in the context of a cell, we work in laboratories like ours at the kilogram scale, building 20-odd cells a day. And by the time we get to the scale at the far right-hand side, which is our gigafactory, that's a kiloton per year of materials that we're processing. And to make that jump from laboratory into full-scale factory, what you need is the ability to trial those manufacturing processes. If you're going to be making 50 cells a second, you want to make sure you're making them right, because if you're losing money off them, then making more is a really bad idea. So what we need here in the UK is a facility that lets us look at that manufacturing journey as well as the scientific journey. And a part of the Faraday Challenge is the construction of something called the UK Battery Industrialisation Centre. And that's being built in Coventry. It's not very far away from my own institution at Warwick. That's a 20,000 square metre facility. It's about 1/10 of the size of a gigafactory, so it's still a pretty significant endeavour. And that'll have the ability to do about 1 gigawatt hour per year manufacturing capacity. And that allows material suppliers, manufacturing companies, car companies to start designing cells, designing new manufacturing processes, and bringing new materials forward to market. And what we hope is that that's going to give a springboard in the UK for a large-scale manufacturer to set up, to link into the R&D and the development efforts here, and start to supply some of the major OEMs that we've got based in the UK. And that, I hope, is a good opportunity to hand over to one of the major OEMs that we have here in the UK.
Thanks, David.